Welcome back, everyone. Today we're going to be building on the past video on op-amp gain stages, and we're going to start looking at how those op-amp gain stages get used in overdrive circuits, particularly ones that use what is called soft clipping. Soft clipping is a way of clipping or distorting the audio signal by putting clipping elements, typically diodes, in the feedback loop of an op-amp gain stage. Two of the pedals that are most famously associated with this are the Marshall Blues Breaker, which is the foundation of the Analog Man King of Tone, and the Tube Screamer, which has spawned a million variants and is found everywhere. So I have here the schematic, which I did not draw this time. I just found this out on the internet from the original 1992 version of the Marshall Blues Breaker. And you can see that really it just consists of a couple of op-amp stages and then a couple of controls here at the output. So let's go ahead and walk through this. So we've got our input, which comes right here, okay? And so this 2.2 meg is our pull-down resistor. This guy is our input capacitor, which is going to block DC. And then we also have this 1 meg ohm resistor right here that has this little dot right here, which is our 4.5 volt bias voltage. Okay, so what this is doing is this is biasing the op-amp because we're coming in on the positive terminal, so this is a non-inverting gain stage. And then we have our op-amp itself, and our output creates a feedback loop into the negative terminal that goes through this 100 picofarad capacitor, and it also goes through this potentiometer. This is the drive pot. This is kind of a clever implementation of the drive pot here, because as we turn the pot clockwise, like we're turning up the gain, we are simultaneously doing two things. The first thing that we're doing is we are making the resistance from the output to this capacitor here go to 0, and we are also increasing the amount of resistance in the feedback loop. And the gain of a non-inverting op-amp stage depends on the ratio of the resistance in the feedback loop and the resistance over here. Okay? Now, we have on kind of this tail of the feedback loop, if you will, we've got a resistor in parallel with a resistor capacitor combo that then comes into a capacitor that goes to our 4.5 volt bias voltage. Now, having these two components in parallel with this component adds a little bit of frequency shaping, okay? Because this capacitor is going to have a frequency dependent impedance, whereas the resistors will show the same impedance over all frequency. Okay, so those in parallel, as well as this cap, result in some frequency shaping. For example, this 27K and this 10 nanofarad capacitor form a high pass filter at this point. Okay. All right. Actually, let's see. I think that's a low pass filter now that I think about it. I can never keep track of which is which. I think when you go through a resistor to a cap, it's a low pass filter, I believe. But lots of resources on the web. We're just looking more at the overall structure of this here. So that is our first gain stage. This gain stage serves to both buffer the signal and boost the amplitude of the signal for us to come into our second gain stage here. So we have a coupling capacitor which blocks DC. That's this guy right here. And then we come into an inverting gain stage. Okay, so the inverting gain stage is going to have its gain determined by, here, let me erase the line I already had up there. It's going to be determined by the ratio of our feedback resistors to our input resistor. Okay, well, you can see that our positive terminal is tied directly to bias voltage, which is very common for an inverting op-amp stage. And then we get to the actual soft clipping here, and that is these 4 diodes. Okay, now a diode only conducts in one direction, but there is a voltage associated with them such that if a signal exceeds a certain level, it's going to start clipping them. And you see here that it specifies small signal silicon diodes. Most small signal silicon diodes have a forward voltage drop of about 0.7 volts, which means that in order to clip a signal in this feedback loop, we would need about 1.4 volts. And the reason you see these back to back here is because we want to clip the positive swing of the voltage and the negative swing of the voltage. If we only had the diodes going one direction, we would only clip 1/2 of the waveform. But one thing we can do is we can actually change the number or type of diodes that are in here. For example, we could get rid of this diode, and we would have 2 in one direction and 1 in the other. This is called asymmetrical clipping. You'll hear a lot about that in a lot of pedals because a lot of people will use it as a buzzword for making things sound, quote unquote, more tube-like. But that is something that you can certainly play around with. You can play around with the number of diodes in their arrangement. You can use LEDs, you can use germanium diodes, you can use Schottky diodes. You can even use MOSFETs, because MOSFETs, when wired up in a particular way, are basically just a diode, because the MOSFET has an internal protection diode. So by the time we get to our output here, we have clipped our signal. We've gained it up through the first stage. We have then sent it through here where it has clipped in the feedback loop. And so now all we have to do is shape and scale the remainder of our signal. So our tone pot here changes the corner frequency of this filter. Okay, this is a low pass filter, which is why when you turn the tone control down, you get rid of all the high frequencies. You're pushing that corner really far down on your low pass filter. Okay, and then after we filter it, we just have our output volume pot and a coupling capacitor, followed by our pull down resistor. Okay, so it's all pretty straightforward now that we understand the building blocks of what we have done before. We see that we just have 2 gain stages, a filter control, which is just, changing the high frequency content, and then we're just scaling it, and we're protecting ourselves from a DC voltage, and we've got our pull down resistor to eliminate pops. Now, if we want to get just a little more complicated, we can come over here to the tube screamer schematic, which I've also just pulled off the internet. And you see that there's a little bit more going on here, but it's not it's not really anything that we haven't seen yet. So let's break it down really quick. We have this input stage here, which is just a transistor stage with its associated components. We have a transistor stage here on the output with its associated components. We have this right here is our first op-amp gain stage. We have a second op-amp stage. And then we have a level control. So really, we've only got 5 basic blocks that are in here. And we've already seen each of these blocks in isolation. So we're just going to step through them pretty quickly here and discuss some of the unique things about this particular schematic. Okay, so we have here our input buffer. Okay, this is not really providing any kind of gain. It's just providing a high input impedance and a low output impedance so that we're not loading the signal down, or so that we're not like losing any of our signal integrity, for example. Okay, so we're not going to get too much into the specific values or anything there. Then we have our coupling capacitor to remove any DC that might be on here. This is just our emitter follower buffer. We have the bias resistor since we're coming into a non-inverting op-amp gain stage. And then in our feedback loop, we've got several things going on here. First, the drive pot is a variable resistance in the feedback loop. And so as we turn the drive up, this resistor value gets bigger, which means the op-amp is going to amplify the signal more. And as the signal gets amplified more, the signal is going to be bigger as it comes through these diodes, which means more of the waveform is going to get clipped because more of the waveform is going to be above that diode voltage. Okay, and then we have a little bit of capacitance here to help kind of tame the high end and to provide some high frequency stability. And then this capacitor and resistor help set the gain of the stage. And the capacitor also provides a little bit of frequency dependent gain for the stage. But on the whole, this soft clipping stage is really not all that different from the stages we've seen in our other schematic. Okay, so then we come through this resistor here. We've got a capacitor. This forms a little bit of a low pass filter. We have our bias voltage getting applied through this resistor here, and it's another non-inverting gain stage. And what we have here is we've got this 1K resistor in the feedback loop, but then we're varying the resistance that comes from this point down through this capacitor to ground. Okay, this resistance here of the tone pot is fixed. So as far as the op-amp is concerned, it's always seeing the same DC gain, but as we change the resistance between terminal 2 and 3 here, we're letting more or less of the signal come through this low pass filter where the corner changes with this pot. Okay, so it's an active tone control because it is in the amplification loop of this op-amp stage, as opposed to just having a pot with a capacitor hanging off the end here. So it's not strictly necessary, but it's the way that it's designed, and it's a design that works well. Okay. Then we have our output capacitor from the second stage through a resistor into our level control. And then we have another DC blocking capacitor. And then we have another emitter follower um, transistor stage. Emitter follower is just a unity gain transistor stage. That's where we've got our voltage that comes in on the collector. We bias the base and then we pull off of the emitter, and there's a resistance from the emitter to ground. So this is just a unity gain buffer here that is providing us with a low output impedance to drive the rest of our signal chain downstream. We have a DC blocking capacitor here, and we have a pull down resistor, and there's our output. So that is all there really is to the Tube Screamer. It's a really great circuit. It sounds great. There's a reason it's been used by everyone and their dog for the last almost 50 years. But now you understand a little more of what it's doing, I hope. I hope you found this interesting. Next up, I am thinking that we'll probably start looking at distortion and hard clipping. So subscribe if you haven't already and stay tuned. We'll see you then. Thanks.